Solving general chemistry problems. Reaction kinetics. What things can influence the rate of a chemical reaction? We can identify at least 5 important aspects. First of all, concentration of reaction participants. Second is the temperature. And the third we will discuss are catalysts. The fourth and the fifth are ones we will not get into in general chemistry, but it's worth knowing that they are there. They are fourth, the solvent system. Now, this is whether the reaction occurs in water as a solvent or using ethanol, for instance. There can be significant differences. And fifth, the surface area of solids. A finely divided metal powder can be explosive, while the same metal as a single chunk is completely stable. We will focus on the first 3 items in general chemistry. First, a word of warning. More so than with any other topic in general chemistry, you will need to learn to understand and interpret graphical data and the tabular data from which the graphs are constructed. Now, this is an important skill for any and all scientists, and non-scientists too for that matter. Always carefully read titles and axes and make sure you understand what the graph is saying. At the minimum, construct a couple of sentences in your mind that describe what the graph is communicating. Now, we could measure the way the concentration of some species evolves with time. However, we are after the rate of change of that concentration at any point in time. More important still is the rate of the reaction itself at any point in time. How do we take the concentration versus time data and produce the reaction rate versus time data? Now, here again is the bromine concentration data we have been discussing. As we've been reminded in the last section, and as you've learned in your calculus classes, the slope of a curve at a point is its derivative at that point. So we choose a point, let's say t equals 20,000 seconds, and draw a tangent line at that point. We can complete the right triangle, and the rise over the run, or delta y over delta x, is the slope of the curve at that point, and it is the value of dy by dx. Now, we can do this for as many points on the curve as we desire and have patience for. We can now graph this value of this slope against time. This tells us how the rate of bromine production changes with time. Now, we've also learned how that rate of bromine production is related to the rate of reaction through its stoichiometry. For this reaction, Br2 has the coefficient of 3, so we divide all of these derivatives by 3 to get the reaction rate. This can now be plotted against time, and here is that curve. So here's a recap of the procedure that we had to follow. Take a close look at the graph of the reaction rate curve. How is it related to the bromine concentration curve, and does it make sense? The reaction rate curve is a plot of the slope of the concentration curve. The first graph plots the concentration versus time, while the second one plots the rate of change in concentration, scaled by the stoichiometry, versus time. The bromine concentration is continually increasing, so its derivative is always positive. The rate demonstrates that. We also see that the concentration data is increasing most rapidly at the beginning, but then slows down as it progresses. This too is very evident in the rate data graph. It starts off with a large positive value that quickly drops to a much lower value as it heads towards 0. The question we now pose is this: can we theoretically explain the reaction rate data curve? Now, this is a major goal of the theory of reaction kinetics. If we have a fixed temperature and no catalysts present, we can write down the form of an expression that relates the rate of a chemical reaction to the concentration of the various reactants. I bring back the bromate-bromide reaction to serve as an example. The general form of the rate law anticipates that it will be a product of the reactant concentrations, each one raised to an as yet unspecified power. There is a constant K to be determined. Its value is unique to the reaction under consideration, and it is also temperature dependent. But since at this point we are considering constant temperature, we can quite rightly refer to K as the rate constant. Just be careful not to confuse the reaction rate with the reaction rate constant. Now, it is a constant throughout the reaction process as long as we keep the temperature constant. Key point: the exponents are not related to the coefficients in the reaction equation. We cannot complete this equation without a lot of experimental data. We will look at ways to determine them from experiments. The rate constant K has a specific value at each temperature. Later on, we will take a look at how it changes with temperature, but it is a constant for each temperature, and it also needs to be determined experimentally. Writing out a complete rate law requires identifying the exponents and measuring the rate constant, K. This equation determines the reaction rate, and recall that the rate is related to the rates of change of concentration of the reaction participants. Now it's important. It is related to them, but it is not the same thing. Remember these relations. Now, a word of warning, or perhaps just explanation. Rate laws are often more complex than this general expression suggests. There can be fractional algebraic relationships, multiple terms summed together, etc. The study of reaction kinetics is a complex and sophisticated field of study. In general chemistry, we seek to introduce you to the field and do so by looking at some of the simpler forms of reaction equations. Simpler perhaps, but nevertheless instructive, so that you might develop a better feel and sense of the field. So to recap, we can measure concentration changes with time. We can find the rate of those changes by taking the derivative of such data. We can relate those concentration rate changes to the reaction rate by the reaction equation stoichiometry. So how can we find a specific rate law from this data? How do we go about taking this bromine-bromate reaction data and determine the specific form of the rate law? Well, we will start by focusing on the exponents x, y, and z, and we will anticipate them to have integer values. The experimental strategy we will pursue will be to perform 2 experiments where temperature and all except one concentration are all held constant. The temperature being constant ensures that K is the same in both experiments. Here's a graph of the rate data for 2 experiments. The first experiment is the reaction rate data we've been looking at for this reaction up to this point. The second experiment is also reaction rate data, except that the initial concentration of bromate is twice that which it was in the first experiment, 3 millimolar versus 6 millimolar. Everything else was the same. What can we conclude? Well, the rate is greater when we increase the bromate concentration, so we can confirm that the reaction rate data does indeed depend upon the bromate concentration. But in what way? Well, it might be hard to tell from the graphs themselves, but at any time point, if you compare the 2 rates, you will see that the second experiment has twice the rate of the first. When we doubled the concentration of bromate, we doubled the rate. Looking back at the general rate equation, that would suggest that the exponent for the bromate concentration, which is represented by x, must have the value of 1. You double the concentration and you double the rate. X equals 1. You can imagine doing a similar experiment for the other reactants, but before we do that, let's think about this data first. Remember that the production of each of these rate graphs involved acquiring the concentration versus time data over a period of almost 2 days, and then finding the derivative of the data at each time point, and then graphing those derivatives. That is a lot of work to just find out that x equals 1. Remember, however, that this relationship holds at every time point in the graph. All 150,000 seconds tell us the same thing. Any one of them would work. Which point has the largest difference and which would give us the best data to work with? Clearly, that is at the beginning of the experiment. Instead of carrying out the experiment for 2 days, what if we just looked at the first 100 seconds, or even less? Would this be sufficient to tell us the rate right at the beginning of the 2 experiments? Indeed it is, and this technique is referred to as using initial rate data. Here is the same bromine data, but only graphed for the first 110 seconds. Where's the curvature, you ask? Seems pretty straight, doesn't it? Well, it is still curved, but it's not very pronounced on this scale. That rapid rise at the beginning, now here's the complete data set again for comparison. That rapid rise at the beginning is quite straight when compared to the complete data set. This is typically the case. This makes it comparatively easy to draw in a straight line tangent at the time t equals 0. With that tangent giving us the slope and hence the derivative at t equals 0, we can, with the equation stoichiometry, find the reaction rate. When we do that with the initial bromate concentration of 3 millimolar, we get a reaction rate, not the bromine production rate, of 1.2 times 10 to the minus 7 molar per second. When we do that with the initial bromate concentration of 6 millimolar, we get a reaction rate of 2.4 times 10 to the minus 7 molar per second. If you're comfortable with your mathematics, you could readily conclude that x must equal 1 in the rate equation. You double the bromate concentration, you double the reaction rate. Other situations may be more complicated, so let me show you how you can work this out mathematically. We write out the rate law for both experiments. The two rates and the two bromate concentrations are indicated by subscripts. Divide the second equation by the first. You can see that it really boils down to just the ratio of the two concentrations, each raised to the exponent in question, being equal to the ratio of the rates, which we find to be 2. We know the second bromate initial concentration is twice that of the first experiment. Substitute this in, and the concentrations cancel. By taking the logarithm of each side, which brings the exponent out in front as a multiplied value, we can solve this for x to find that it is equal to 1. At many points along this calculation, you may have noticed that x would equal 1 and you could stop there. But if it is ever more complex, this more thorough approach will give you the result. But in general chemistry, we will usually encounter more straightforward questions that will be readily answered by inspection alone. So now we know that x equals 1. Here's the rate equation again with that information included. We need to do the same kind of experiment again, except this time hold bromate and hydronium ion concentrations constant and double the concentration of bromide. We go back to bromate concentration being 3 millimolar. The bromide concentration is 5 millimolar and 10 millimolar in the two experiments. What is found? A doubling of the bromide concentration produces a doubling of the rate. Can you see what that value for Z means? Well, Z must be equal to 1 also. Here's the updated rate equation. The next step, do a similar experiment, but with the hydronium ion concentration. Keep bromate 3 millimolar and bromide at 5 millimolar. Do experiments with H plus equal to 10 millimolar and then 20 millimolar. What do we get? Now this is different. A doubling of the H plus concentration led to a quadrupling of the rate. If you think back to the math, this would imply that log of 4 over log of 2 is equal to y, which equals 2. Concentration of H plus is squared. The rate law now has this form. And finally, what is the value for K, the rate constant? Remember that it's constant throughout this reaction for all concentration combinations as long as the temperature is constant. This is an easy one. Take any concentration combination for which you know the date rate. Substitute in everything and solve for K. Use the very first set of data for the t equals 0 data point. We substitute in and find that K at this temperature equals 80. The units of K are molar to the minus 3 seconds to the minus 1. Note that the units for K will be different depending upon the structure of the rate equation. However many concentration terms raised to whatever exponents, the units of K, which is rate constant, must always work with the concentration terms so that the rate always ends up having units of molarity per second. So in general chemistry, how do we usually encounter these questions? Generally, you are not asked to analyze raw data, draw in tangent lines, find slopes, etc. It is important for you to remember the relationship between a rate of reaction compared to the rate of change of the concentration of reaction participants. And it is important to be able to take some initial rate data and find exponents and rate constants. Here are some of those kinds of questions. For the following reaction between nitric oxide and hydrogen at a certain temperature, it was found that the rate of disappearance of hydrogen was minus 4 times 10 to the minus 3 molar per second. What was the rate of the reaction at this time? Two things to remember. A reaction rate is always positive, so the negative rate measured for the hydrogen loss must have its sign changed because the reaction is always viewed as going forward. Also, as shown by the reaction stoichiometry, 2 hydrogens disappear for every full reaction event. So the reaction rate must be 1/2 the hydrogen rate. Reaction rate is equal to 2 times 10 to the minus 3 molar per second. Now consider this reaction. At a certain temperature, the hydrogen consumption was found to be minus 4 times 10 to the minus 3 molar per second. What was the rate of reaction at that time? Oh, wait a minute. Isn't this the same reaction as above? Sure enough, except the reaction is written with different stoichiometry. What counts as the reaction is now different. Indeed, when this reaction process occurs twice, the old reaction process will have occurred once. So we apply the same reasoning and find that this reaction rate is 4 times 10 to the minus 3 molar per second, or twice that found previously. The difference, however, is a result of how we defined the reaction differently. The rate of hydrogen consumption was the same. It could care less how we write out the reaction equation. But the way we relate that to our reaction equation does make a difference. Here again is the reaction between nitric oxide and hydrogen. This time, you are supplied with some initial rate data. Work out the following. In the rate law, what will be the exponent for the NO term? What will be the exponent for the H2 concentration term? Write out the rate law, determine the value of the rate constant K, and what is the reaction rate at a point when the NO and H2 concentrations are both 5 millimolar. With these kinds of questions, first find the exponents, find two experiments where only one component is changing, compare the change in reaction rate to the change in concentration. In this case, experiments 1 and 2. Notice that the H2 concentration is constant. At the same time, the NO concentration is tripled from 2 to 6. And the initial rates? Now watch the exponents in the scientific notation carefully, but the rate goes from 0.005 to 0.015 molar per second. Now that is a threefold increase. Concentration triples and the rate triples. The NO exponent must be 1. Then in experiments 1 and 3, NO is constant while H2 triples from 4 to 12 millimolar. The rate goes from 0.005 to 0.045 molar per second, which is a 9-fold increase. Concentration triples while rate increases. 3 squared equals 9 times. The H2 exponent is 2. The rate law is therefore K equals concentration of NO times concentration of H2 squared. Take the data from experiment 1 to find the rate constant, rearrange the rate law to solve for K, don't forget the H2 is squared, and watch the units carefully. We have K equals 1.56 times 10 to the 5 molar to the minus 2 seconds to the minus 1. Finally, the rate given these conditions just requires substitution into the rate law. We get that the rate is 0.0195 molar per second. Here is another similar problem. This time the reaction of study is between nitrogen dioxide and fluorine, which produces nitrile fluoride. Now, nitrile fluoride, by the way, is a strong oxidizing agent and has been considered for use in rocket propellants. Here is some initial rate data. With this data, determine the rate law and calculate the value for the rate constant. Experiments 1 and 2 tell us that the exponent for nitrogen dioxide must be 1. Experiments 2 and 3 inform us about the fluorine dependence. The fluorine concentration drops in experiment 3, watch that, and the change in concentration is by a factor of 2.5. As that is also the change in rates, we can conclude that the fluorine exponent is also 1. Here is the rate law. Now, any of the 3 sets of experimental data could be used, but I use that from experiment 1. It leads to a value of K equal to 40 molar to the minus 1 seconds to the minus 1. Now, one more problem. The reaction this time is between carbon monoxide and nitrogen dioxide. The products are carbon dioxide and nitrogen oxide. Understanding this reaction is important for its role in atmospheric pollution studies. Here is some initial rate data at some particular but unspecified temperature. Again, find the rate law and determine the value for the rate constant K. Experiments 1 and 3 are used to confirm that the NO2 exponent is 1. Now, something to note here in the calculations. We are looking for integer exponents. We want our data to be able to tell us that it is 1, not possibly 0 or 2. You will notice that we end up comparing 2.34 with 2.33 raised to the x. So I declare the answer for x to be 1. The slight differences in this case arise from some rounding off errors. But you may also get some questions where some experimental error is included in the data. The fact that it is not exactly 2.33 is not a concern. From the choices of 0, 1, or 2, the obvious answer is x equals 1. So now, what about the other species, the CO? But experiments 2 and 3 should reveal the influence of the CO concentration, but the rate does not change. This indicates the exponent of the rate concentration of CO is 0. Anything raised to the power of 0 is just 1. CO does not appear in the rate law. Here is the rate law. It only depends upon the concentration of NO2 raised to the first power. The rate constant is calculated to be 0.0217 seconds to the minus 1. The lesson here is that a reaction may consume some chemical species, but that species may not control the reaction kinetics. This is because all reactions are a sequence of multiple elementary reaction steps. In this case, the step that controls the kinetics must not involve CO. There are other steps that will still continue to consume CO, but they are very fast and do not dictate the kinetic velocity of the reaction.